Welcome back, everybody. This is part 2 of our videos for 3.1 on implicit differentiation for Calc 1, fall 2023. This was originally done live, and I forgot to hit record when we came back from break. So this is going to be a little expedited because you can pause the video here, and it's not for class. Our next problem that we're going to work on with implicit differentiation is the Folium of Descartes. It is x cubed plus y cubed equals 3xy. We will find the tangent line at 3 halves, 3 halves. We can come look at what the folium looks like real quick. I think it's worth seeing. X cubed plus x, not x, but y here, equals 3xy. So it kind of looks like a string with a knot, but as it gets further away from the origin, it's a straight line. Looks like almost like y equals negative x, but it's a little off. But that's what the folium looks like. So we're going to take a look at that. We're going to find the tangent line at 3 halves, and we're going to write and find where in quadrant 1 the tangent line is horizontal. So first thing we do is we're going to take the derivative. And so we're doing it implicitly. So we're going to take the derivative of x cubed is 3x squared. The derivative of y cubed is 3y squared. We're going to treat the y cubed as a function. Take the derivative, it's 3y squared. And since the variable is y, not x, we have to have a dy dx. The right side is a product rule, 3x times y. So y is like f of x here. And so we have 3y when we take the derivative of x first. Then we take the derivative of y. It's 3x times dy dx. Then what I did is I collected dy dx all on the left side. And I factored out 3y squared minus 3x. And then I divided by 3y squared minus 3x. And I got 3y minus 3x squared over 3y squared minus 3x. You will notice we can divide top and bottom by 3. We can factor out a 3 and then divide by it. And we get y minus x squared over y squared minus x. Now the denominator can't equal 0. So we got to keep that in mind. We want to look at where what's going on the tangent line at 3 halves, 3 halves. So we're taking 3 halves, 3 halves. We plug that into dy dx. So that was our function right here. We're plugging 3 halves into this for x and y. And that's what we get. I didn't actually solve what or calculate what the top and bottom were because I recognize that the bottom is just the top backwards. So I factored out a -1 so that we can cancel those out. And we're left with -1 over 1. I can do that here now. Those go to 1 each, and I'm just left with -1 over 1, which is -1. So then we have y minus y1 equals m times x minus x1, where we're plugging in 3 halves for this, 3 halves for that, and -1 for that. That gets us there. And I solved for y, and I got that equation right there. Y equals -x plus 3. The next thing we wanted to do was find where in quadrant 1 the tangent line was 0. Or horizontal, we had a horizontal line. The horizontal line has a slope of 0. So that's what we're looking for right here. So we're going to set our dy dx equal to 0. Because dy dx can help us calculate the slope of the line. Now, we don't want the bottom to equal 0, so y squared minus x can't equal 0, which means y squared cannot equal x. If we get a solution where y squared equals x, we have to reject it. Fair enough? Like we can't have 1, 1. So, at this point, solving for 0 basically becomes where does the top equal 0? That's where a fraction equals 0, where the top equals 0. So where does y minus x squared equal 0? When y equals x squared. And so we're going to take y equals x squared and we're going to plug it back into our original equation. This shows us graphically where that line is going to be at. It looks like it's going to be right there. If we did a horizontal line right here in quadrant 1, we're gonna hit it. Be right there. That'll be our tangent line, would be horizontal right here. So we want to find that. We're going to do that by plugging in to our equation what's going on. So plug x squared in for y over here, which I did here. I did it just as parentheses first. And then I cleaned it up. And I get x to the 6 minus 2x cubed equals 0. You can either do a u sub for u equals x cubed, which is the easiest way to go, until you're really good at doing this substitutions on your own without having, or solving these without having to use substitutions. You should do a u substitution. So if I make u equal x cubed, then u squared is x to the 6th. And my equation becomes u squared minus 2u equals 0. Where does that happen? When u times u minus 2 equals 0, which means u equals 0 or u minus 2 equals 0. So from there, we got to plug x cubed back in. We have x cubed equals 0 or x cubed equals 2. The first one gives us x equals 0. And when x equals 0, y equals 0 in the starter equation. First off, that's the origin. It's not even in quadrant 0, really. It's on the border of quadrant 0, but it also violates y squared cannot equal x. So we're tossing that out for a multitude of reasons. We have x cubed equals 2. We can solve for x equal x by taking the cube root. And then I'm just going to use, rather than plugging it in up here, I'm going to take x equals cube root of 2, plug it into y equals x squared, and that's what I got here. Cube root of 2 squared, because we're squaring it. And so I get y equals the cube root of 4. So that's where our value is. That was that weird point we had. It was the cube root of 2 and the cube root of 4 over here graphically on the line. Whatever that is. Not showing where they intersect very well. It's not snapping to it like it normally does. Okay. So that was the folium of Descartes. To use implicit differentiation, we assume a couple things. We assume y represents a function of x that is defined explicitly by the given equations. And we also assume that the function defined implicitly is differentiable. Those are two assumptions we use when we're taking implicit differentiation. Sometimes you can do the derivative implicitly, but it's meaningless. So if either of these assumptions is wrong, the result can actually be nonsense. For example, x squared plus y squared plus 1 equals 0. We can solve this implicitly. We can do implicit differentiation. But if we solve for x squared plus y squared, we get x squared plus y squared equals -1. X squared plus y squared is a circle in the xy plane, where the right side is the radius squared. R squared equals -1. R is plus or minus I. It's not a real number. And radius needs to be a real number because it's a distance. So this is kind of meaningless. X squared plus y squared equals 1 is kind of meaningless. And so, like, implicit differentiation doesn't really work here. So, and it's not really noticeable unless you were to solve for x squared plus y squared right away. Sometimes we get meaningless results. I know I'm talking fast because I know you can rewind and pause, and this video doesn't need to be longer than it needs to be. Let's take a look at 3.2. 3.2 is on the derivative of logarithmic functions. So we're going to start with the natural log of x, and we're going to use the definition of the derivative. Limit as h goes to 0 of f of x plus h minus f of x over h. So we do that here. I got the limit as h goes to 0 of natural log of x plus h minus natural log of x over h. I like to factor the 1 over h out. And some of you did this on the test. You just tried to cancel x's and say this was 1 plus h over 1. That's bad. This is not 1 plus h over 1. You cannot cancel out x's, okay? So you're seeing some rusty algebra skills in here. You guys got to beef up on that, okay? What we can do is we can split it into two fractions. I can make it x over x and then h over x. And now x over x can be 1. That cancellation works there because there's no plus sign in the fraction messing it up. Notice I keep writing limit each time. You need to write limit, keep writing that limit as h goes to 0 each time until you actually evaluate the limit. I saw a lot of times on the test, people wrote it down one time and then it never showed up again. Despite all this work they did, the limit never showed up again. You need to keep writing limit until you evaluate, because otherwise you're showing that it's not clear what you're doing. And you're not presenting the information well. And it's not clear you know what you're doing. Okay? So we get to this point, and this is like a hard spot to work with. So I don't like it like this. Like, I don't know where to go with this. So I'm going to set h over x equal to b. If I set h over x equal to b, I can solve for h here by multiplying both sides by x, and I get h equals bx. As h goes to 0, b goes to 0. So I can rewrite this limit as the limit as b goes to 0, and then the h out front is vx, so 1 over vx, natural log of 1 plus v. B is the variable here that we're doing the limit with. X is a constant, and so like I can factor out a 1 over x. So I'm going to factor out a 1 over x, and I have 1 over x times the limit as b goes to 0 of 1 over v, natural log of 1 plus v. Rules of natural logs is we can take this and raise it up top like an exponent. And so that's what we're going to do. And then our limit laws also say that we can pass limits inside natural logarithms. So we get the right side here, 1 over x times the natural log. And then we're going to do the limit as v goes to 0 here of 1 plus v to the 1 over v power. Here we can evaluate. This is where we're going to plug in v. As v goes to 0, that goes to 0, and 1 over 0 goes to infinity. So we've got 1 to infinity. 1 to infinity is just 1. So this entire natural log here equals 1. And the result of the derivative of natural log of x is 1 over x. I just wanted to point out here, that's the takeaway here. We need that. Where else does the natural log equal 1? E. So this must be right here, must be another way of defining E. Limit as v goes to 0 of 1 plus v to the 1 over v power. So we can define E using this weird limit. It's kind of neat. Now that we've taken a look at natural logs, let's do regular logs. We're going to use this to speed it up. So we're going to take the derivative of log base b of x. Remember, the change of base formula is we can, if we've got some base we don't like, we can do log. This could either be natural log of x over natural log of b, or the other preferable choice is log 10x over log 10b, because both of these can be done in a calculator if you have values for them. That's the change of base formula, though, switching from this over to one of those. We did this already, natural log of x. We took the derivative of that, so we're going to work with that. Natural log of b is just a constant here, so we can factor the constant out. And we have 1 over natural log of b equals the derivative of the natural log of x. We already showed this part here was 1 over x. Boom. So we're going to write it as the derivative of log base b of x equals 1 over x times the natural log of b. All that on the bottom. Okay? There's a lot going on here. I hope you're pausing the videos to record this while you need to. Let's find the derivative of the natural log of x squared plus 4. Now, until you're comfortable just doing a chain rule right away, I recommend doing u equals x squared plus 4. And if we do that, we have the derivative of the natural log of u. And that, if we do that, we need to multiply by du dx for the chain rule. Chain rule. Okay, so du dx is 2x. The 4 goes away. I was seeing this in some tests. Taking the derivative of a constant, people were leaving the constant. It's gone. Don't leave it there. So, oh, I wrote it again here. Look at that. So we've got derivative of natural log of u is just 1 over u. And du dx is 2x. We're going to take u equals x squared plus 4. We're going to bring this and plug it back in. And we're going to get 1 over x squared plus 4 times 2x is 2x over x squared plus 4. Now, you can do this without a u sub. Like I said, you can do it without a u sub. You can do the chain rule, but it requires a little bit more mastery with the chain rule. And with practice, it comes faster. I recommend trying to do it without the u sub first. Like in your homework, do it without the u sub. Try to do this with the chain rule, and then do a u sub and see what the answer is with the u sub, because the u sub is definitely easier, but it takes more work. It takes more writing. To do this without a u sub, we're going to focus on doing the derivative of the whole thing first. Just the derivative of natural log is 1 over whatever's inside. So 1 over whatever's inside is 1 over x squared plus 4. Then we have to take the derivative of what's inside. So we're going to take the derivative of x squared plus 4. We multiply it. It's not added or subtracted. It's multiplied. That's another mistake I saw with the chain rule. So we multiply it, and we quickly get to that without all that u step over there. So it is doable. It just takes some practice. One more quick little blurb. I want you to find the derivative of, this is a big thing, natural log of x squared cosine x over the square root of x plus 1. I recommend doing u for a u sub. This is I don't even know that I would want to try to do the chain rule without doing a u sub, because there's a lot going on here. There's a product on top. This is a quotient. I could do this all as a triple product. I could write this as x squared cosine x, and then x plus 1 to the square root of that on the bottom. Oh wait, I need to have the x there. And then I could have x plus 1 to the negative 1/2. So this is like, if I wanted to do product and chain rule only without a quotient rule, I could do that. I'll call that g of x real quick. you could take the derivative of this, but like this is like A, B, and C. So you got to take the derivative one at a time. I'm going to do this in person. I want you to try to do this at home. We'll finish it Tuesday morning. For the quotient rule, remember that it's high prime low minus high low prime over low squared, or d low or high d low minus or low d high minus high d low over low squared. I like this one. Looks like the product rule. H is the top, L is the bottom. I recommend writing it down and making sure you're writing down correct. H stands for high. L stands for low. It's supposed to give you the information from it. I also saw this on the exam. People were writing down H was the denominator and L was the top, which kind of, it'll make your quotient rule flipped on top. You'll have the wrong sign, but then you're taking the square of the wrong thing on the bottom. So that's bad. So go ahead and try to solve this. We'll solve this first thing on Tuesday. Peace.